Thank you for inviting me. I just wanted to say actually that the previous talk I thought was great, a really good call for action around privacy. I'm going to sort of move along in that direction a little bit and talk particularly about zero knowledge proofs and then how they can be applied to machine learning. Now the notes for this are available. Hopefully you'll be able to scan that. That will take you to this website, maths.xp.io. There's links in that to a number of talks, so you get lots of talks about other things about maths, etc. But for this talk, I've actually got far more than I'm going to be able to cover, so I'm going to skip through some parts of it. And it is intended as really an introduction. And what I want to talk about is really what is ZKML itself and what challenges do we face with it. What frameworks are out there to help us build using that? What is the sort of the state of the art? What are the latest developments? And if you're interested, where you can go from here, what you can do. As I say, it's a gentle introduction. So some of the notes you'll see get quite complex, but I'm going to skip through a lot of those and really just concentrate on the beginning part. Okay, so machine learning. So that's an aspect of artificial intelligence. Fortunately, I'm sure you're all very familiar with machine learning. You've probably all used large language models yourself, so I don't have to say too much about it. One point I need to talk about, though, is that there are two parts I want to talk about with machine learning, or two processes. The first one is the idea where we train a machine learning model to do something. And then the second part, that once we have that trained model, then we can use it. So when you're using your large language model, your ChatGPT, etc., it's already been trained and you are using it with its configuration already in place. And that's when you're doing that, when you're using it once it's trained, that is called the inference stage of machine learning. So yeah, I talked about the idea of this model. So this is something that is going to be trained on some input data, and hopefully it's going to be able to generalize. It should be able to be trained to take on training data, and they'll be able to apply that and do something useful with new data, which is really what we want. This can be a very involved process. The training in terms of computation is much greater than is needed when we do the inference stage, when we're actually using these parts. So in terms of the components, many machine learning models are built of neural networks, and they're built in layers. So we'll start off with an input layer. We'll have these things called hidden layers, and there will be many of these, and then we have some output. And what the training is doing is setting up the links between the nodes within these layers and setting up the weights that they're within those layers. More particularly, it looks like this. You have inputs coming in. Each of the nodes in the network will have weights. They are then, as you are doing the inference stage, those are multiplied by the inputs. We then come to the sum of all of those. We then run a function over that called the activation function. And for each node in the network, so for each one of these circles, it will then decide whether it's going to pass on an output to the next layer or not. Okay. This is very much simplifying things. Also, we have the possibility of doing bias as well. So this is something that doesn't depend on the input, but it's kind of tweaking one of these nodes to change its value. All right. Now, in terms of the size of these things, the large language models we have now are huge. So if you think of those weights, so each of the inputs going to the next layer has a weight. With large language models now, they are running with hundreds of billions or even trillions of weights. And the number of layers is hundreds of layers. So these things are absolutely huge. But they are very useful. They seem to work very well. All right, so but we're concerned with privacy. Why would we want that with machine learning? What's the point? So maybe we will have some confidential data that we're using for training, so we want privacy around that. Maybe the actual parameters, when we've trained this model, maybe those parameters have business value. and you wouldn't want other people to know how you've trained your model and the result of that training. And then also, when we're using the model, the input that you're providing to the large language model or whatever type of machine learning, that could also be confidential. Now, I won't ask for a show of hands, but I imagine you've probably used things like ChatGPT. You've typed in a prompt. Most people will do that and really not care what happens to that information that they send in there. But some people may worry about that. Of course, it depends on the data. You'll probably be happy asking it to write a small piece of code for you and doing a very simple prompt. But then if you start to put in information that could be confidential or have business value, then we start to see that privacy can be important. So what can we do? Well, we could just do everything locally. We could just do everything in private, which will be possible, and then you're guaranteed to have privacy. And in fact, this kind of comes back to some of the questions from the last talk about how can we get privacy in blockchains. There are blockchains that do this, that do off-chain computation. But we could do that anyway with our large language model. But what if we want to be able to share the model in some way, or maybe we want to be able to share the training of the model? We may want our model to be trained using the experience that other people have had in other models. And is that possible to do? And I'm going to answer these questions. Okay, so zero-knowledge proofs. I'm going to skip through a lot of this, but basically they allow us to do some verifiable computation. And the important part is that having done some computation, come up with a result, we can verify that is correct and do that succinctly, much more quickly than it would take to do the whole computation again. Otherwise, there wouldn't be any point. That's one aspect of them. The other aspect is that we can do computation over private inputs. So I could do some computation using some private data. I could send the result of that to someone, assuming that I don't mind them seeing the result. And I could also send them a proof that that computation had been done correctly. And they wouldn't be able to reverse engineer it or find out what the inputs were. Okay. I'm going to skip through more details about those. This is just showing some of the different types of framework zero-knowledge proving systems we have. We have Starks and Snarks, etc. There's a great article, The Cambrian Explosion. Do take a look at that. All right, so ZKML, is this really anything more than just getting some buzzwords and putting them together? We've got ZK, which is very popular. We've got machine learning. We've just put these things together. Does it actually give us anything? Well, yes, it does. So we can do computation and verify that. So maybe we can verify some of the computation that is being done within the machine learning. But also, perhaps we can do machine learning with some privacy as well and still get results that can be verified. And I've got some potential use cases here. There are lots. Really, any way or anywhere that you would want some privacy, then that could be used. Things like private KYC, so for financial systems, identity systems where you want some kind of differential privacy. Lots of applications in DeFi. Healthcare, obviously, because we want to have patient data being kept confidential, etc. This diagram here represents, this is a little bit old, but it does represent some of the ecosystem in ZKML as it has developed. Not all of these things are still around, though, but I will be mentioning some of them. Certainly on the hardware side, there's quite a lot going on. There are companies building special chips to do ZK and cryptography and do that very efficiently and very fast, and that's being used for ZKML as well. We see some very interesting use cases. I don't know if people are familiar with WorldCoin. Don't think they're here, but you often see them at conferences. They have an orb that will scan your retina, and it allows them to create an ID, but it allows to keep the biometric information private. Okay. Now, challenges. So, machine learning, that's just some computation. We've trained our model. We're going to run that model against some inputs. That's just doing some computation, some sums, etc., doing the activation function. ZK is good at proving computation, so it should be a piece of cake just to put these things together and get the ZK to verify that computation. Unfortunately, it's not the case. And this comes, two main reasons. One is complexity. They're both very complex areas, so getting them, making sure they're working correctly is not trivial. But the biggest problem we really have is to do with the underlying mathematics that these depend upon. So machine learning involves creating large matrices, doing lots of floating point operations, using floating point numbers, doing sort of everyday maths. Zero knowledge proofs are much more restricted. When we do zero knowledge proofs, we restrict the types of numbers that we use. We operate on integers, we operate on what are called finite fields, so these are sets of integers that have a maximum value. This means we do modular arithmetic. The zero knowledge proofs work, but only because we are restricting ourselves in the type of maths. So when we try to put these two things together, we've got a major problem, that the underlying representation is not the same for both of them. One way you can get around that, I'm just mentioning here, the idea of quantization. You could have a floating point number, and you could effectively multiply that up until it becomes an integer. As long as you remember how much you've multiplied it, then that would work. So we could do that, but obviously that's an extra layer that we're adding to the whole system, and that is affecting the performance of it. You can do quantization generally, where you just kind of miss off some of the precision, and in machine learning that does happen, but then your machine learning model doesn't end up working as well as it could do. So that's a problem. Another point is determinism. Zero knowledge proofs have to be completely deterministic. They have to have exactly the same result, no matter who does it or where, or for the proof to be valid. With machine learning, now in a way they are deterministic, but the way that they are used, they often introduce randomness. So, for example, if you're using things to generate images, they often use randomness within that. And ZK really doesn't like the idea of randomness. It doesn't work well with that. And I just want to say, I really like this final quote here. Reality has a surprising amount of detail. I think that's a great thing to bear in mind. Okay. So, with ZKML, people are trying to do this. So I don't want to be too pessimistic. It's not hopeless. So people are making progress. But where we're doing that is on the inference stage. The training stage, because that is so computationally complex, that's still very difficult to do and create proofs of, just because it takes so long. What would it look like then if we do some ZKML, and where would you use this? Well, this is a diagram from a ZKML framework called TensorPlonk, and the idea behind it is that we have someone who wants to use a machine learning model. They're the consumer, and they are providing an input X, and they're outsourcing the machine learning to somebody else. So they're relying on somebody to do the machine learning for them. That person takes that, has the weights in their model, that takes the input that our consumer has done, and creates some output. But with ZKML, we can also create a proof, and we can create a proof of how that computation was done. And we can prove things like, did they use the correct model? If you send off your data to run through a machine learning model, then maybe they will use the best model, but maybe they'll use some cheap model and all that kind of thing. So you want to know, that it's been done correctly. So once we have that proof and the output, that can go back to the consumer, and they can check then very quickly that the machine learning was done correctly. How do we actually do this? And can we easily model something like a neural network in zero knowledge? If you do it in a very naive approach, and the way that we've used zero knowledge generally, it's very difficult. Okay. So we have to do a number of tweaks. I'm going to have to skip through a lot of this, but we can tweak the way that we do ZK to try to make it more machine learning friendly. Another way we can do it is to use recursion, use recursive proofs. That works kind of nicely because we have all these layers, and you can recursively go through the layers of a neural network. So that's one approach that is useful. if you're looking to build something with ZKML, one of the best frameworks, one of the best libraries is Ezekiel, which allows you to do that. You can take an existing an existing model, machine learning model. Maybe you've written that in TensorFlow, something like that, and then you can use the Ezekiel library to create zero-knowledge proofs from that. So this is one of the I think the most practical ways that we can do this at the moment. I won't say much more about that, other than to do this, you have to put the model in a standard format, which is the Onyx format. Okay. I'm just going to skip through the rest of it. Some of the latest research people have done, this was a project where, because we have this problem of weights within the model, people have worked out ways to do machine learning without weights, and that's where we have the zero gravity. Also, let me go on. Yeah, I'll just mention this also. This happened last year. So we had this view that it's too complex. We can't do ZKML easily. But last year, people have done this. They did manage to prove GPT-2, which is an earlier version, but it had more than 1 billion weights, and they managed to get that they managed to create a proof from that. The actual proof itself, it took 90 hours to set up the system, and then the proof itself took 90 hours to compute, so it's not great performance, but they managed to do it, so that was a step forward. Okay. Another approach has been used, GKR. I'm not going to talk about that. That gets quite complex. But we have, people doing, so ZKDL, people are building special tweaks and changing the way we do ZK to work better with machine learning. So there's lots of links here into papers to show you how that can be done. Also, Nethermind have come up with this ZK system called Zinc, which doesn't rely on integers. So it changes the maths that we use in ZK, so we can use rational numbers. So that's something else that can help. The other approaches, there's optimistic machine learning, I won't go into that. Federated machine learning, these are other approaches. But finally, I've got some links for you if you want to find out more. WorldCoin that I mentioned earlier, they have great resources. There's links there to their introduction. The Zero Knowledge podcast is always good for anything zero knowledge, but also ZKML. There's links there to lots of different projects. We are also, we run courses, and we have an academy that's just starting. This is going to be some online courses that you will be able to do. If you find me here tomorrow, I can give you a discount code for those courses as well. All right, I think I'm probably out of time. So thank you very much for your attention, and I'm happy to answer some questions.
So do we have, yeah, there is a question over there.
Thank you for your presentation. I have a question regarding application of ZK proving or any kind of proving in machine learning. How far are we from real implementation? What are your thoughts about that?
Well, we can do this. So for example, with Ezekiel, you can do that. You can take some models that you've written just using standard machine learning and create proofs from that. But at the moment, the problem is performance. It just takes a long time to create all of this. So for machine learning models that are complex and very large, it's quite difficult at the moment.
I'm aware of that, so I'm asking what are your thoughts when it will be applicable in sense of, okay, in 2 years, 4 years, or how you envision that?
So people are making advances. We're doing tweaks to the cryptography, etc., that's helping. So I think within 2 years, maybe we'll get to be able to do some of the simpler large language models that we have at the moment. Because we've already done ChatGPT-2, so we've passed 1 billion weights, so we've managed to do that. Okay, in 90 hours, but that's not great. But so I think, in a couple of years, we'll probably be starting to do things reasonably on some of the models we see at the moment. There's always going to be a gap, though. By that time, the models will have increased again.
There is a lot of room for improvement, essentially.
Yeah, there is.
Thank you.
Yeah.
Thanks for the presentation. I'm not familiar with all of the different neural network types, but as far as I know, there are different kinds and they have different structures. So I'm wondering, I know about ZKCNN, it was the only paper that I actually read, but does it really differ from different neural network types, in terms of benchmark or in terms of the success of the proof systems to to actually have verifiable ML? Because I'm wondering, okay, ZKCNN was good and could be improved, and the other work that you have presented, my actually kind of I wasn't sure about if all these methods gonna be applying to every single different ML models, or ML types, let's say. So I would be happy if you could answer that.
Yeah, sure. Yeah, I think that's a good point. And I think with the way that things are improving is that they are taking some, say, some specific techniques. So with convolutional networks, they're taking techniques of how they work and then improving small parts of that. So I think we're not going to see, it's not going to be sort of moving, everything moving together at once. We're probably going to see specific types of of networks and neural nets going at different paces as they manage to sort of tweak various aspects of them. So yeah, I think that's very valid.
Thank you. Also, another short question, quite similar to the previous one. Is there a better approach to accelerate the ZK in terms of ML, than hardware acceleration right now? Because I'm not sure, the tweaking cryptography is it that promising, or hardware acceleration is the best hope? Also asking as a FHE researcher, so I understand your pain.
Yeah, so I think hardware is going to help, but a lot of the work that's going on is on the cryptographic side and looking at the way that we actually create the zero-knowledge proofs and getting techniques there better and more adapted to what we want, to the architecture of neural networks. So yeah, we're not relying just on the hardware. Yeah.
Thank you.
Okay.
Thank you. Maybe a bit more technical question. You mentioned in machine learning models that most of them using neural networks, matrix multiplications. Is there a consensus on the kind of zero knowledge part? Which kind of proofs are best for this? Is it going in one direction, elliptic, curve-based, or recursion-based, or whatever, or it's very diverse and not really moving in just one direction?
So So recursion, I think, is very promising, but recursion generally in zero knowledge is perhaps at an earlier stage than sort of the standard types of snarks, for example. So some techniques that have been useful are using things called lookup tables, which have been used in zero knowledge proofs anyway, but they work particularly well in solving some of the problems we have with machine learning. But in terms of things like are Starks better or snarks, I don't think that sort of at that level there's anything I could say, but some very specific techniques do work better. But I think recursion, for example, particularly because we are seeing quite a breakthrough on the sort of folding scheme side as well, I think there's a lot of potential there. I think that will help out. Yeah.
Thank you.